The next thing is to talk about noise in RLC networks, and this occurs quite often in practice. So, in other words, we have already seen what happens with noise in a resistor. It turns out, as I was mentioning the other day, capacitors and inductors are noiseless. So, if you have an RLC network, what it basically means that you have a network with any number of R's, L's and C's, okay, and every resistor is associated with a noise source, which we denote by Vn sub k, and this is the output, correct. So, what is S Vn? Let us call this SVk of f is what? Is simply 4 kT times R sub k, the units being volt square per hertz. All right. So, it seems it's obvious that now if you have a whole bunch of resistors and you have this black box and then you get two terminals out, the voltage, if you put a voltmeter across these two terminals, what do you expect to see? What would you expect to see? If you put a voltmeter across those two terminals, you will have obviously noise, because there are a whole bunch of noisy elements inside the box. And how will we find the noise spectral density at the output? Well, it's very straightforward. What do we do? I mean, the step by step approach is to simply find the transfer function from every noise source to the output. Let us call that h sub k of f, correct. And what is the spectral density corresponding to the kth noise source? It is 4 kT R sub k times mod h sub k of f the whole square. All right. This will be the in English, what does this stand? What does this mean? What is that quantity there? That 4 kT R sub k h k of f the whole square. What does that represent? The noise spectral density at the output due to the kth resistor, right? And we also discussed that the noise from different resistors is independent. So, if you want to find the noise spectral density due to all the resistors, it is simply what? It is a sum over all resistors. So, simply sum over k R k h k of f the whole square. All right. Okay. So, well, there is one aspect of the whole problem that we have not exploited yet. What is that? Well, this is true for any network, right? If you have multiple sources, you find the noise spectral density at the output due to each source and you add them. What is new? There is nothing new here, right? There is one aspect of the problem that we have not exploited yet, and what might that be? The network consists only of R, L and C, and therefore, what we have not exploited is, once you have a network like this, there is also, one aspect is that it turns out to be reciprocal. And so, basically, that is what we are going to exploit next. And so, to see that, so let us say this is a current the current I, alright. What comment can you make about the transfer function from here to the current in the kth resistor? Well, if this is I, this will be, or rather let us say this is a phasor of angle 1, angle 0, what will be the phasor here? This phasor is simply h sub k of f times 1. Is this clear? Correct? Alright. So, the next thing I would like to draw your attention to is the looking in impedance here, let us call that Z of f, alright. So, what comment can we make about the energy supplied or the power supplied by this current source into the box? What comment can we, I mean, if you have a current driving into an impedance Z of f, right, okay. So, what comment can we make about the energy supplied by the current source into this box? Pardon? I square times the real part of, very good. So, basically the power going in is basically I square, fortunately that happens to be 1, times real part of Z of f, right. So, where is all the power inside the box being dissipated? It is being dissipated in the resistors, and well, do we know the current through the resistors? Right, that is nothing but Hk of f. So, what is the power dissipated in the kth resistor? Yes, mod Hk of f the whole square times Rk. So, what is the total power dissipated in all the resistors? It is simply the sum over all k, and that must be equal to, does it make sense, people? Alright. So, so now can you stare at these two equations and tell me what conclusion you can draw from this? Pardon? Yeah, so what comment can we make about the output noise spectral density? So, SVO of f is simply, put 1 and 2 together, you get 4 kT times the real part of 0. Alright, and this is what is called Nyquist theorem. I guess it must be called one more of Nyquist theorems. Right? And so, for example, let us come back to our familiar example here. We already know the answer, and all right. So, what comment can we make about Z of f r by 1 plus j 2 pi f r c, real part of Z of f is r by, yes people, 1 plus 4 pi square f square r square c square. Okay. So, SV of f is simply 4 kTr by 1 plus 4 pi square f square r square c square. well, this and this is volt square per hertz, and we knew this answer already, right, where earlier we had actually calculated the transfer function from the noise source to the output and done the math. It turns out that we could have done this way. Is clear, people? Okay. So, all right. So, what comment can we make about the total noise? That is VO square is simply the integral of SV of f df, and which is simply nothing but 4 k T integral what, people? Real part of z of f okay. And as we have already seen, the real part of z of f df is this, and if you integrate this, we did the integral the last time around and we found it to be k T over c. All right. Now, it turns out that in a lot of practical situations, we are only interested in the total mean square noise. Okay. In other words, so far, I mean, let us kind of backtrack a little bit and see what we have done so far to determine the total noise. What have we done? Yes, can you remind me what we need to do? Very good. So, we have gone and found the transfer functions from each noise source to the output, right. Then there must be noise somewhere, no? The transfer function is got nothing to do with transfer function is transfer function. So, we need to multiply, we need to find the transfer function from every noise source to the output, right. Multiply, find the magnitude squared of that transfer function multiplied by the spectral density of the noise source, and then that will give us the output noise spectral density due to one noise source, and you find the sum over all the noise sources, right. That will give you the noise spectral density at the output. Now, you have to integrate this noise spectral density across the entire frequency range 0 to infinity to be able to get the total mean square noise. Is this clear, people? Right. So, I mean, in other words, if you found the total noise spectral density, let us say is like this, you are basically finding the area under the curve, right. So, this is SVO of f and this is f, and basically what you are doing is finding the area here. Now, does somebody see this as being kind of long winded and perhaps unnecessary? See, we are only interested in finding the total area under the curve, right. The exact nature of the curve is irrelevant. So, it does not make sense to find the exact spectral density, which is a lot of work, right. Why is it a lot of work? We have to calculate the transfer function from every noise source to the output, all right, and then find the square transfer function. And I mean, just in case, since most of you have this, why is this so difficult look on your face, okay. So, let us call this R1, C1, R2, C2, all right. The transfer function from this noise source to the output will have it's a second order denominator, right. So, the denominator magnitude square will be a fourth order polynomial, right. And so likewise, the transfer function from Vn2 to the output, let us say this is the, we are interested in finding the total noise across C2, that will also be a fourth order polynomial, and then you need to find the integrals of these fourth order polynomials across 1 over those fourth order polynomials across all frequencies, right. And this is only for a second order network. Let us say you had 5 capacitors and 4 inductors, and then you have all of a sudden you have a 9th order transfer function, correct, which means the squared magnitude response will have 18th order polynomial in the denominator, right. So, all the tricks you learnt in your JEE and GATE coaching classes, which basically right are of no use. Okay, all right. So, but the fact remains that, oh well, I mean, so here is an analogy, right. Let me ask you a question with respect to the circuit on the right. What is the order of that transfer function? It's a fourth order transfer function. Let's say I want to find the DC gain from Vi to Vo, right. This is Vo. What comment can we make about the DC transfer function from Vi to Vo? 1, right. Okay. How did you can you give us some insight into the dramatic speed with which you were able to get the answer? Excellent, right. I mean, so this is common sense. What you would do is basically say, oh well, the capacitors are open at DC, the inductors are shorts, the answer is 1, right. You could also do it this way, which is not very uncommon by the way in exams, right. You could find the whole transfer function, fourth order transfer function, and then put S equal to 0 and get the answer to be 1, okay. So, this finding the area under the curve, right. To find the area under the curve, to write the magnitude response, square it and integrate it from over all frequencies, right, is to do a whole lot of work to get the details of the spectral density at the output, and then throw away 99% of that information, and since you are only interested in the area under the curve, right. That is exactly equivalent to finding the transfer function, I mean corresponding to this network. If somebody asks you what the DC gain was, is to find H of S and then plop in S is equal to 0 and be very happy that, oh, most of the terms vanish, correct. Okay. So, again fortunately it turns out that this if you are only interested in the total area under the curve, or if you are only interested in the total mean square noise, it turns out that it seems reasonable that you do not have to work as hard to go and find the actual spectral density, right, which basically means that you are working very hard to get a lot of information and then throwing most of that information away because you are only interested in the area. I mean, all of you understand that, there is a lot more information in the exact shape of the curve than in the area. Is this clear, people?